So we're going to go through section 1.3, which is about complex numbers. So right now, the set of real numbers doesn't include all the actual numbers that we need to use in algebra. So for example, you won't have a real solution to x squared equaling -1 or x squared equaling -4. So pretty much you can't take a real number, times it by itself, and get something negative. So because of this, we've got to define the complex number system. So an imaginary unit, I, is going to be utilized to help us solve equations where something squared has to equal a negative quantity. So I is going to be defined as the square root of -1. So if you go ahead and square both sides, I squared itself is -1. So this way, when we have a radical when we have something squared being negative, we'll know it has to be some type of imaginary number. So because of this, we have something called a complex number. It's going to be a number in a specific form where it's got an imaginary component to it. So it's going to be a plus b times I, where a and b themselves are real numbers. So like 3 plus 7i, 4 minus 3i. It's got a real part to it, this a, and then you've got a piece that's imaginary as well. So we say a is the real part and b is the imaginary part. So complex numbers are going to help us solve different types of equations where you get something squared equaling negative. So let's go ahead and let's try to get some practice writing these square roots in terms of imaginary numbers. So we've got the square root of -9. So what we want to do is use our properties we know with radicals. But I want to pull that minus sign out somehow. So you can write -9 as -1 times 9. Break apart those two radicals. And so the -√1 becomes I, and then the square root of 9 is 3. If we look at the square root of -48, we need to break this down as much as we can. So 48 we can break into something dealing with a perfect square. 16 times 3 will be 48, but you still have that minus sign in there, so you want to pull off the -1. So the square root of -1 becomes I, root 16 is going to be 4, and then this we just have to leave under the radical, so it becomes 4 root 3i. So we can do the same type of things. We can still multiply, divide complex numbers. We can FOIL stuff out, but you have to be a little bit careful when you go through that process. So here, if we want the square root of -17 times the square root of -17, it's going to be really natural for you to just want to multiply what's underneath first. And then if you try to do that, it's going to make that positive or that negative disappear, because the minus times the minus will give you a positive. What you want to do first is pull out that -1. So go ahead and write root -17 as root 17i. Same thing for the second expression. Pull out that -1 as the imaginary piece. Because now I can multiply the like things. We can multiply the root 17's together and the i's together. So you get the square root of 17 times 17, and then I times I is I squared. So you're getting the square root of 17 squared, and I squared we know to be -1. So this ends up equaling -17. So you have to be careful when you go through this process. You don't want to apply the same thing you did before. You don't want to immediately pull these under a radical and do -17 times -17, because those minus signs would end up disappearing and you now no longer have complex numbers involved. So just be careful with these types of problems, okay? So you can only use this property if they're both not negative. So if one's negative and the other is positive, it's perfectly fine. But the best thing you can do is write everything in terms of I before you go through simplification. So same thing when you're dealing with division of radicals, pull out those imaginary pieces. So in both of these, I'm going to take out that -1, so an I will pop out. And since I'm going to get an I in the numerator and denominator, they cancel. Now what's left over, I'm able to work with because these are both real numbers. So you can put those under a single radical, and then 70 divided by 10 is 7. So this simplifies nicely into the square root of 7. Now when we want to add, subtract, or just combine any type of complex number, you're going to do the same thing as before. You can only combine like pieces. So you can't add x squared and x because they're not alike. Same thing, I can't add the real part and the imaginary part together. I can only add the real parts of each expression. So here, if I'm adding two complex numbers, I add the real parts together, and then we also add the imaginary parts together. If you're subtracting, same thing. You subtract the real parts, and then you go ahead and you subtract the imaginary parts as well. So we want to make sure we write our answer in a very specific form because you need to pick off the real part and the imaginary part, and they need to be separated. So this is called standard form. A complex number should be in the form a plus bi. So if we look at some simple examples, 7 plus 9i, that's in standard form. A is 7, b is 9. When we look at 7 over 2 plus 9 over 2i, that's in standard form because you immediately know a and b. However, when you look at this one, that's not in standard form because I don't have distinct values of a and b. I've got to do this division operation first. So it's very, very particular. You need those real and imaginary parts to be separated. So finally, let's go ahead and let's perform each of these operations and make sure our answer is going to be in standard form. So we're going to start with 4 minus I plus 8 plus 5i. So I want to go ahead and I want to combine the like pieces. So here's my real part, 4 and 8. We're going to go ahead and add those together. So my new real part will end up being 12. And then I've got negative I plus 5i. So I've got negative 1 plus 5 more I. So this complex number is going to be 12 plus 4i, which is in standard form. Now if we go through this one where we've got a real part, we've got an imaginary part, and then we're subtracting two more complex numbers, best thing we can do is go ahead and distribute out that negative first, and then combine based on the different pieces. So distribute out the minus signs, and then we'll group. We've got a real part, real part, real part. So in total, we've got negative 13 as our real part. Then I've got negative root 2i plus 4 more root 2i's, so 3 root 2i. Add up one more, and in total, we've got 4 root 2i. So again, in standard form, it's separated appropriately. Now, if we want to multiply two complex numbers, remember the way you multiply two binomials is by going through and FOILing out those terms. So FOILing deals with the first, outer, inner, and last. So I want to go through and I want to look at the first terms. So that's negative 2 and positive 4. And we're going to multiply those together. Then we'll go for the outer terms, which is negative 2, negative 2i. Multiply those together. Then we go through the inner, which is 3i and 4. Multiply those together. And finally, we've got the last terms, which is 3i and negative 2i. Multiply those and add them as well. So now we go ahead and simplify, multiply those out. When you take 3i, multiply by negative 2i, you get negative 6i squared. Now we can go ahead and replace I squared by negative 1 and then group our like pieces. So we've got 4i plus 12i, so in total we've got 16i. Negative 6 times negative 1 is positive 6. So then when we add the real numbers together, we get negative 2 plus 16i. Okay. Now when we're dealing with division, it's a little bit harder because I can't split this denominator when it's addition. It's only when it's multiplication can you split it into fractions. And you can split addition across a numerator. But I can't go ahead and write that this is 6 plus 2i over 1 plus 6 plus 2i over 2i. This is a really common mistake, and you want to be really careful about doing this. It does not work that way when it's in the bottom. So what we actually need to do is we need to find a way to get the bottom to disappear or condense to a single number that you can multiply by. So a really useful tool is going to be multiplying by the conjugate. So if you have this imaginary number, its conjugate's going to be found by changing the sign on the imaginary part. So we can go ahead and utilize a nice property then, because when you multiply a complex number times its conjugate, when you do the first terms, you get a squared. The outer will be negative ABI. The inner is positive ABI. So those end up canceling out. And then the last term is minus BI squared, which really just becomes positive B squared. So for this expression, I want to go ahead and I want to multiply the bottom by the conjugate. But since I'm multiplying the bottom, I've got to do the same thing up top. So we need to go ahead and actually FOIL both of these out. So if we multiply the top out by FOILing, we'll get 6 minus 12i plus 2i, and that'll be minus 4i squared. And in the bottom, if you go through that process, your first term's 1, your outer's negative 2i, your inner's positive 2i, and your last is negative 2i times 2i. So the positive and negative 2i's cancel. So in the bottom, we're going to be left with 1 minus 4i squared. Then we can also group our like pieces. So I can combine the negative 12i and 2i. And then I squared itself is negative 1. So both of these I squareds will become negative 1. And then it's a matter of just simplifying, combining the real parts. So I can add the 6 and the 4 together to get 10. And in the bottom we get 5. But we need to make sure this thing's in standard form. So I need to separate it into 2 individual fractions. So you get 10 over 5 minus 10 over 5i. Or really, that's just 2 minus 2i. So this is in standard form. Back here, this one is not. So if you're getting answers wrong and you're not 100% sure why, it's probably because you don't have it in the right form. You always want to get it in standard form.